Now that we've seen how to combine functions, there's a formula you're going to learn called the difference quotient. It's a very useful formula in calculus. It's kind of a foundational formula, and so it's good to learn it now. It doesn't require any calculus to do it, just a basic understanding of functions and function notation. But it's good to kind of learn this topic now so that you're prepared for those of you who may be going into calculus. So the difference quotient is a formula that looks like this. It is f of x plus h minus f of x, so it's two functions subtracted, all divided by h. Now you might ask, what are all these symbols, right? What is the x, what is the h, what is the f? Well, in calculus, what you'll find is that you'll have these graphs showing up. Okay, it's a graph of a function. And on the graph, if you took 2 points and connected them with a line, we call that a secant line, you can find the slope of that line essentially using this formula. The slope of that line, basically, if you take the 2 points, you look at the coordinates of the 2 points, the first one we'll call it x because it's on the x-axis, right? And the second one, what we'll do is we will add a distance to it. So this distance we're going to add is h. Okay, so the second point is x plus h, right? It's the first one plus the distance. And so the corresponding outputs are going to be over here f of x, right? It's the y value when you plug in the x. And the second one up here is going to be f of, well, the input is x plus h. Right, so you get x plus h as the input, so it's f of x plus h. Now if I wanted to find the slope of this thing, remember that the slope is the rise over the run. It's the change, it's the vertical change or the change in the y values divided by the horizontal change or the change in the x values. So we call that rise over run. Well, in this particular diagram, the rise from one point to the next is the difference in these two function values, f of x plus h minus f of x. It's the difference in those two numbers. The run is the difference in the x values, the difference between x plus h and x. Well, we have the distance there, it's h, so that's what goes in the bottom. So we have the rise over run for those 2 points. And that's how this formula is derived and what it means. Now, you don't really need to know that, it's just kind of interesting information. What you guys need to know is how to calculate this if you're given a function. Okay, so if I give you the equation for this curve, how could you calculate this difference quotient? Okay, so that's what we're going to practice. So let's take a function. We'll do a couple examples, but let's make one that's not too bad. Maybe 3x plus 4. Okay, just a linear function, not too crazy. Well, this function here, in order to find the difference quotient, I need to find all the parts and then combine them. So I'm going to start off by finding f of x plus h. That's the first chunk here in the difference quotient. Well, f of x plus h, all that means is that the x plus h is your input. That expression replaces the original x. Whatever's in the parentheses goes in for x. So this x would become 3 times, the x becomes x plus h, and then plus 4, right? So instead of 3x plus 4, it becomes 3 times x plus h plus 4, okay? So the x plus h replaces the original x. Then you just distribute and simplify that. So this would become, what, 3x plus 3h plus 4, right? Okay, so that's the first chunk. So we're going to replace the f of x plus h in the formula with this function. F of x we already know, that's this function. So we have both pieces to the numerator. So if I wanted to find the full numerator, f of x plus h minus f of x, I just subtract these two functions from each other. So the first one is 3x plus 3h plus 4. And the second one, so then I'm going to subtract, the second one is 3x plus 4. Okay? So now we just distribute and simplify, right? Distribute the minus and simplify. So we get 3x plus 3h plus 4 minus 3x minus 4. Combining like terms, I've got a 3x minus 3x, those add up to 0. I've got a 4 minus 4, those add up to 0. So all I actually have left is the 3h. Okay? So that means my entire numerator is nothing more than just the expression 3h. So if I want to find that whole expression with the h on the bottom, so f of x plus h minus f of x all over h, well, the numerator is just 3h, right? We just calculated that whole, complicated looking expression on top just simplifies down to 3h. Then I have the h on the bottom. Well, there's a common factor of h. I can cancel those h's off, and we're left with just a 3. Okay? So the difference quotient for the function 3x plus 4 is equal to simply 3. There are some very interesting patterns that show up in calculus that allows you to bypass some of this calculation and jump to the answer. We're not going to show you those here. I really just want you to get used to using the formula and combining things appropriately. Now there are many different types of functions. I gave you a simple linear function on this first one. They get more complicated. We can have fractions in our function. We could have roots in our function. We could have logarithms in our function. We could have trig functions. We're not going to go through a lot of those real complicated ones, but you'll see some like roots in this section. So let's do a couple more examples where we show this. And I'm going to need a little more space. I'm going to rewrite that formula off to the side a little more. So it is f of x plus h minus f of x all over h. Now, I'm not expecting you guys to memorize that formula. I would put that on a test if you needed it at this point. Okay. If I ask you to calculate the difference quotient, I'll put the formula there with the problem. Okay, so that's the difference quotient. So let's take, do f of x equals, let's do 5 over x. Let's try something like that. It's a rational function, so it has a variable in the denominator. Okay, so let's try to piece together all this information. The first thing we need is f of x plus h. So f of x plus h, remember, the x plus h is what's going to go in for the x in the original function. So this x in the bottom gets replaced with x plus h. Now h is, remember, just that distance that the function is moving. So it's a number, really. We treat it like a number. It's a variable, a number. They're really the same thing. So we treat them the same way. Okay, there's not really anything we can do to simplify this. And so the next step is to put them together using the subtraction. So f of x plus h minus f of x. That's going to be the second one, 5 over x plus h, x plus h, then minus, then the first one, f of x, which is 5 over x, okay? So that's our subtraction. Now this we could combine, and it's going to be important to combine these into one fraction. To do that, I need a common denominator, an LCD. Here I look at the factors of these two denominators, and they don't have anything in common, right? So the x plus h is the only factor on the first one, x is the only factor on the second one. Because there's no x plus h here, and there's no x by itself here, they don't have any common factors. So the LCD is going to be the product of the two denominators. Okay, so the LCD is just going to be x times x plus h. Okay, the two factors multiplied. So to get an LCD on the first fraction, I'm going to multiply the top and the bottom by the missing factor, which is the x. That's what's missing there. And on the second fraction, I'm going to multiply the top and the bottom by the entire quantity x plus h, because that is the missing factor on the second fraction. Okay, so when I do that, the first fraction just becomes 5x. Try to color coordinate a little bit here. 5x over the LCD, which is x times x plus h. Now I could distribute that and call that x squared plus xh. I'm going to hold off on doing that. I'll show you why in a moment. Then the second fraction becomes 5 times x plus h. Now here on the numerators I am going to distribute them because I'm going to have to combine terms here in a moment. So this will become 5x plus 5h all over the denominator, which I'll keep again factored x times x plus h. Okay. When I combine these fractions, the two numerators combine together. I can combine the terms there. Before I do that, I have to distribute the subtraction across. So I'm going to make these into one fraction. It's going to be 5x minus 5x minus 5h. All right, so the minus distributes to both terms on top. We're subtracting the whole fraction there. Then the LCD remains on the bottom. So it would be x times x plus h. Okay, now here I'm going to combine like terms. 5x minus 5x, those add up to 0. So I can drop those off, and we're going to have a negative 5h over x times x plus h. Okay, now the reason again that I left this denominator factored is because there are times where these fractions will be reducible at this point. If this was a 5x instead of a 5h on top, I could cancel the x's out. So it's possible that keeping these factored could help us to reduce or simplify this further at this point. It's not on this example, but it could on another example. Okay, so here, there's nothing that we can cancel, nothing can simplify any further, and so I guess that's it. No, it's not. That's it for the numerator. Haha. Almost forgot to finish the problem. So this is a fraction, but it is equal to just the numerator of my difference quotient. So this whole fraction is going to go on top. So let me rewrite this. Actually, I'm going to need a little more space. So I'm going to erase a little bit of this. Yeah, I'll erase a little bit more. Okay. So when I write out my difference quotient, f of x plus h minus f of x all over h, the numerator is this thing that we just found. So it's going to be a negative 5h over x times x plus h. But I still have this extra h on the bottom. Okay, so I have my numerator over h. Okay, now when I see this, I see a fraction inside of a fraction. And when we have fractions inside fractions, we call them complex fractions. And to simplify those, we use the multiplying by the reciprocal idea. Remember, this big fraction bar is a division. And when you divide fractions, it's the same as multiplying by the reciprocal. I often call it copy dot flip because it's kind of catchy and I like it. So I'm going to copy dot flip on this. Now to do that, I need to make sure both of these are fractions. So I'm going to write the h as h over 1, so it looks like a fraction. And then I'm going to do the copy dot flip. So I'm going to copy the first fraction down. That would be negative 5h over x times x plus h. And then here's where the dot flip comes in. I'm going to multiply by the reciprocal of that denominator. So it's 1 over h. Okay, so I'm flipping that fraction. So multiplying by the reciprocal of the h over 1 is 1 over h. Okay, at that point I can cancel. I have a common factor of h on both the top and the bottom. And so I can cancel those h's out. And so my simplified form is going to be negative 5 times 1 is just negative 5. My denominator is simply x times x plus h. Oops. And that's it. That's as simple as this one gets. So I could circle this. That would be a good answer, a nice simplified answer. You could, in theory, distribute that denominator as well. It wouldn't be wrong. It would just be more than you really need to do. I prefer the factored form. But you could, if you wanted to, write it as negative 5 over x squared plus xh. That would be okay. But again, I prefer the factored form. It's just less for you to have to do. Now remember, one thing that's really nice about this is that it doesn't have an h by itself in the bottom. It does have an h on the bottom, but it's h within a factor. It doesn't have its an individual factor of h on the bottom, like the original difference quotient does. There's a reason that that's nice. And so when we simplify these, our goal is to eliminate that h from the denominator, if possible. In calculus, it's going to be very important to be able to do that. There are times where we can't, or where simplifying doesn't really allow us to get rid of the h, but that's going to be one of our goals. As we'll see shortly that there may be some examples where that can't happen, but here we can. We got it to cancel out, and that's really nice. Okay, so let's try another example. We'll choose one that has a root in it next, just so you can see how that works out. Okay, so let's try something like equals the square root of, I don't know, x plus 1 maybe, something like that. Just not too crazy. So square root of x plus 1. So again, we're going to break this down in steps. We're going to find f of x plus h first. Well, f of x plus h, again, remember, you just replace the x with x plus h, so it becomes x plus h plus 1. Okay, so the x becomes x plus h. That's it. I can't simplify that. They're all unlike terms. So what I'm going to do is I'm going to then subtract the two functions. So f of x plus h minus f of x, that's going to become the, the square root of x plus h plus 1 minus the square root of x plus 1. All right, that's it. I can't really do anything with that because everything's under roots. You can't split roots up when they have sums and differences under them. You can if they're multiplied or divided, if you have a product or a quotient underneath. But with adding and subtracting, we can't really split those up. So we got to leave it. So now I want to take that and put it over h, because that's my numerator. So this thing, let's bring it down here, is going to become the square root of x plus h plus 1 minus the square root of x plus 1 all over h. You're thinking, well, that It's just complicated, it's ugly, I don't know what to do with it. And yeah, it's all of those things. But again, remember, we want to get the h out of the bottom somehow. We want to cancel it out or do some stuff to make that happen. When dealing with roots, it's very important to remember a little trick called rationalizing. Okay? Those of you who remember your trigonometry courses, you probably learned this, and probably in some algebra courses too. I'll do it in a different color here. This is a separate example. Rationalizing means if you had something like 3 over the square root of 2, if you want to rationalize the denominator, you would have to multiply by that square root of 2 on both the top and the bottom. And what rationalizing does is it gets rid of the roots. Okay, so this at least on the bottom, right? If I rationalize the denominator, it eliminates the root from the denominator, moves it to the top. So this becomes 3 root 2 over, well, root 2 times root 2 is 2. It's root 2 squared, and the root and the square cancel off. Okay, so we've rationalized the denominator. Well, if there's more than one term, rationalizing requires a little trick called multiplying by a conjugate. If I had 5 over 3 plus root 2, then in order to rationalize this denominator, you have to multiply by 3 minus root 2. Okay? So you multiply top and bottom by the conjugate, which is 3 minus root 2. Those minuses don't look real good there. Okay? Conjugate just means it's the same two terms, but with a sign change in the middle. Okay? And what happens when you multiply by the conjugate of something, the root disappears. So on top, you would have just the 5 times 3 minus root 2, and that you could combine if you wanted to. But on the bottom, when you distribute, you get 9, you get minus 3 root 2, you get plus 3 root 2, and you get minus 2 when you distribute or use the FOIL method there. The two terms in the middle, minus 3 root 2 plus 3 root 2, add up to 0, so they cancel out. And you end up with 9 minus 2, which is just 7. And all of a sudden, I have no roots on the bottom. That's the goal. Well, here, the reason I'm going through this is because in this example, I want to rationalize the numerator. Okay, I'm going to rationalize the top, which just means I'm going to multiply the top and the bottom by the conjugate of this. Well, the conjugate, it has two terms. They're pretty ugly looking terms. But the conjugate is just a repeat of the two terms with a plus in the middle. Just change the sign. So I would multiply by the square root. I'm going to squeeze this in here. X plus h plus 1. But instead of a minus, I'm going to make it a plus, the other root, x plus 1. Very, very close to the edge. Oh, there's a glare on the screen. You probably can't even see what I wrote there. That's the square root of x plus 1. And I'm going to do the same thing on the bottom. Here I've got a little bit more room. So it's x plus h plus 1 plus the square root of x plus 1. Okay, same thing on the top and the bottom there. When I do that on the numerator, I'm going to expand that out. Get my blue marker. I'm going to have this first root times this first root. Well, they're the same thing. And a root squared gets rid of the root, and so this becomes just x plus h plus 1. Okay, that's the first term times the first term, the f in FOIL, if you will. If I do the first term times, so the outer two, right, first and last, that's going to be a positive root of x plus h plus 1 times the root of x plus 1. So it's the product of the two roots. Then the I in FOIL is going to be the subtraction of the product of the two roots. I'm not going to fill it all in. But because this term and this term are the same except a change in sign, they drop out. Okay, so I don't really need those. The last term, the L in FOIL, is this root times this root. It's the same thing, x plus 1 and x plus 1. So again, when you multiply two roots, it eliminates the root, and you just get the x plus 1. Okay? And so really what I have in this numerator is, oh, I should probably write the denominator in. The denominator is h times all that stuff. I'm going to leave it off. We know that thing is what goes in here for right now. On the numerator, I have, let's see, x plus h plus 1 plus x plus 1. Well, combining like terms, that's x plus x is 2x. The h doesn't combine with anything. The 1 and the 1 make it 2. Right? That's my numerator. The denominator has h times that fraction, which is, let's see, not fraction, I'm sorry, that radical expression. So it's x plus h plus 1 under the first root plus the root of x plus 1 in the second one. Okay? Okay, so the only thing left that we can really do here is we could split this fraction into 3 fractions. Now, I'm not going to actually have you do this. This would be as far as I'm going to have you go. In calculus, however, so I'm going to call this one done. But remember, I don't have the h gone from the bottom. The h is still in there. And it actually looks pretty complicated, even in comparison to what we had at the beginning. In calculus, what we would need to do is split this up into 3 fractions and then simplify each one separately. But we would have another feature called a limit that would be involved that would help us out with that. We don't have access to that in this course because we haven't gotten to limits yet. That's a calculus topic. So we're going to have to stop here. However, it is good to practice this idea of rationalizing the numerator, so to speak. That is an important skill and something that I want you to have some practice with. So this is as simple as it gets. Again, it is not simple. It doesn't look nice, but it is correct. Okay, so that's where we're going to go with it, trying to rationalize the numerator.